Okay, in this example, we're asked to determine the pressure at 4 different locations, points 1, 2, 3, and 4, in this kind of weird shaped container. This is a pretty straightforward problem. The thing to keep in mind when you work through this is that the pressure is only dependent on the depth from the free surface. Doesn't matter if you move laterally, it's only the depth, the distance downward from the free surface. Really, it's in the direction of gravity. So for example, if we're going to find the pressure at point 1, it'll be the pressure that you start with at the free surface here. That'll be atmospheric pressure right here. This is a free surface here, a free surface there. So it's the pressure you start with, so that'll be P atmosphere, plus, we're going to assume that this is a liquid with it's incompressible, plus the density times gravity, so that's the specific weight of the liquid. So I'll just write it as gamma. Gamma is just the specific weight, which is just density times gravity, times the depth to that point. So as we go down to this point 1, that's located at depth h1 from the free surface. So this will be just gamma times h1. So there you go. There's the pressure at 1. We can do the same thing for the pressure at 2. It's the pressure we start with. It'll be P atmosphere. We're going to go from this point down to point 2, and the depth there is h2. So that'll be plus gamma h2. Notice it's a plus because we're adding the weight of the fluid as we go down to the point 2. Really what this hydrostatic pressure relation is just a force balance. The pressure at 2 has to be larger than the pressure that we start with because we're supporting the weight of a column of fluid that's all just kind of sitting above it here. That's the way you can imagine it. So the pressure down here has to be larger than the pressure here to support the weight of all the fluid sitting up there. So pressure at 2 is the pressure we start with. That's what's pushing down from above, plus the specific weight times h2. That's related to the weight of fluid in this column. So that's why P2 is larger than P atmosphere, because we're adding in the weight. So there's the pressure at 2. Now let's do the pressure at 3. There, we're going to start with pressure at atmospheric. So now point 3 is over here. So what will happen is, if you look, point 3 is a little bit higher than the free surface. You can see that right here. So we're actually removing weight to get to point 3. So it'll be P atmosphere minus the specific weight times h3. It's minus because as we go upward, we're removing the weight of the fluid because we're moving upward. So it's actually a little bit lower pressure than what you start with. And notice it doesn't matter that we moved horizontally into this kind of other part of the container. It's just the depth from the free surface. So the depth from this free surface or this free surface is minus h3 to get to point 3. Lastly, for point 4, that one's just located at the same depth as point 2, so that one will actually look exactly the same as the pressure at 2. It'll be P atmosphere plus gamma times h2. And it's because it's still at the same depth from the free surface as point 2 was. So that's it. That's all there is to it. We'll go ahead and end it there.